Hello, and welcome to the wonderful world of physics. My name is Neil McCarthy, and I will be the instructor of this online course. This course is called Physics. We're actually teaching Physics A, and we'll be using this textbook, which you're looking at here. It's called Physics. It's the Principles with Applications. It's by an author named Douglas Giancoli, and it's the 7th edition of this particular textbook. So just a little bit about me. I've been teaching at Wentworth since 1997. I'm an adjunct faculty member, which means I teach 1 or 2 courses per semester, and this particular semester I'm teaching this fully online course. I have my master's in physics. I've been teaching physics for about 25 years. And I have a great enthusiasm for physics, and I hope to share that with you. So physics is basically the study of motion and energy. So if you've never had a physics course before, this course will deal with objects which are moving, and through time we found that there are formulas which govern how everything moves, and in this course you'll be taught how to use those formulas and how to make predictions as to how certain things are going to be moving with time. Okay, so we'll be studying chapters dealing with motion, acceleration, free fall. We'll be dealing with something called vectors. We will be dealing with something called projectile motion. We'll be dealing with forces and forces of friction and forces of objects sliding down the ramp, or forces as something is accelerating vertically up or down. We'll be studying something called work and power and energy and conservation of energy. We'll be studying impulses and impulse forces and momentum. We'll be studying conservation of momentum with collisions, elastic collisions or inelastic collisions, and we'll be studying something called circular motion. So those are all the different topics involved with this course, and the book, as I said, is the 7th edition of Physics by Douglas Giancoli. Okay, so just in chapter 1, we use something called the SI system, which is the System International, and it is basically the metric system. So trying to be standardized with everybody else doing physics, we won't be using things that you know and love. We won't be talking about lengths in terms of feet and inches or miles. We have to talk about lengths in terms of meters. And we won't be talking about speeds and velocities in terms of miles per hour. We would have to be talking about those in terms of meters per second. And we won't be able to be talking about time frames such as a day or a week or a year or some number of minutes. Every one of our time frames has to be converted into seconds. So that's the idea for the beginning of this course. So let me open up the book to show you the standard units in physics. Okay, so if you open up your textbook, I'm looking at page 10. And on page 10, we talk about the 7 base units that exist in physics. That's all there are. There's only 7 different base units. And in this particular course, we only need to use the first 3. In fact, for the first 3 chapters, we only need to use the first 2. So some of the standard units in physics, I just talked about it. Length. We would like to use possibly, if we're measuring a piece of wood, maybe we're going to measure a certain amount of inches, or maybe we're going to measure it in feet and inches. But in this course, we have to use the idea of meters. We have to convert it. If we're talking about driving a certain distance, we'd probably be talking about miles. In this course, we have to convert it into meters. The other thing is, in this course, the standard unit of time is going to be the second. Like I said, most people in everyday life don't refer to upcoming meetings in terms of seconds. People would talk about how many hours away, how many days away. If you're going to meet somebody, how many minutes from now would you meet them? But in this course, we have to talk about time in terms of seconds. So even if we talk about the Earth going around the sun, we would say 1 year. But if you use standard units of seconds, you'd convert that, and it comes out to be approximately 31.5 million seconds it takes for the Earth to do one complete revolution around the sun. And those first two are the only ones we'll be using for the first 3 chapters. We can get more units by manipulating those two. We can multiply them by each other, we can divide them, we can square them. So we can do a lot of different things and come up with many different units based on those two. The one called mass is going to be talked about in chapter 4, and we'll use mass from that point on. So mass, we talk about how much mass a certain object has. We use the standard unit of kilograms. Kilo is a prefix, and kilo by itself means 1,000. So mass is dealing with a kilogram, which is 1,000 grams. Okay, and in the book, it's on this same page. It's on page 10, but it's also in the in the front cover of the book. So if I go to the front cover of the book, I'll show you we have this prefix here. And what you can see is basically these numbers here are multipliers. So if you hear somebody saying kilo, then you're looking basically right here, and kilo means it has a small letter K for a symbol, and it means the number 1,000. If you're talking about mega, it has a symbol of capital M, and it basically means 1,000,000. So for instance, I've zoomed in here a little bit. So when we talk about kilo, kilo is a prefix that means 1,000, and as you can see all the way over here, the multiplier for kilo is 1,000. And we use the small letter K for a symbol. Mega, when people talk about winning megabucks or mega millions, the word mega is a prefix which we add a capital M in front of anything, and it means 10 to the 6, which is a number of million. So if we're talking about megabucks, we're talking about $1,000,000. If we talk about a computer with megahertz, then it's doing 1,000,000 operations per second. If we're talking about a storage capacity of megabytes, that means it has 1,000,000 bytes of storage capacity. And nowadays computers are going bigger and faster, and with the storage and the speed. So giga is a prefix which a lot of people know. Giga means 10 to the 9th. Use the capital letter G for giga, and 10 to the 9th is a billion. So when they talk about gigabytes, it's 1,000,000,000 bytes of storage data, and gigahertz would mean moving with 1,000,000,000 operations per second. And tera is now they're getting storage devices so many terabytes. So if you see something with the capital letter T before it, we could talk about it as times 10 to the 12th, which would be a trillion. So in this prefix table, things get bigger. They can also get smaller. If we saw things in terms of centi, you talk about centimeters a lot. So a small letter C in front of a number, that's a fraction. That's 10 to the -2 power, which means 1 over 10 squared, which is 1 over 100. So when you're talking about a centimeter, it has 100 small centimeters in a meter. Same thing with milli. When we talk about millimeters, it is talking about 1,000 small millimeters are in a meter. And as you probably know from life, micro is talking about the very small, and nano is talking about the very, very small. So those are some prefixes that we use. So before I move on, there's something called derived units. So a derived unit is a unit that's made by multiplying or dividing or somehow or other manipulating other types of vectors. So let me write some of those down. If we were to take something called speed or velocity, in our world, we usually talk about miles per hour. So a typical thing would be miles per hour. But we can't do that here. So the standard unit for miles is talking about a length. So this right here would be talking about a length. And this thing down here would be talking about a time. So when we go and we talk about standard units for speed or velocity, we'll be talking about units of meters per second. Okay, and we write that as meters per second. Okay. When we talk about acceleration, in our world, we might hear someone saying, my car can go from 0 to 60 in 3.8 seconds. What they're implying is my car can go from 0 to 60 miles per hour in, let's say, 4 seconds. That's what they're implying. So somebody might say, my car can go from 0 to 60, and they mean miles per hour. And then they say it can do that in, let's say 4 seconds. Okay. Well, we're not gonna do that. Miles per hour. Miles is a length. And hours is a time. And seconds is a time. So what we're looking at is we're looking at a length divided by a time divided by a time. And in this class, we write it this way. Meters over seconds, all over seconds again. Okay, so that'll be the standard way. Let me erase the wrong way. So another way to see this is we usually write it this way. Meters over seconds squared. So that right there would be the standard unit for acceleration. And there's other ones. We don't use them for a while, but a unit of force is called a Newton. And 1 Newton is equal to 1 kilogram times meters over seconds squared. So that's what we end up getting as another derived unit. It's a derived unit because it's based on kilograms, which is the unit of mass, and it's based on this unit here, meters over seconds squared, which is the unit of acceleration. So if we have something that's accelerating a mass, we say that there is a force on it, and that's how we come up with this unit of force. Okay. Okay, chapter 1, section 6 talks about how to convert units. So basically in this section, we basically have to be able to learn how to turn every single thing into a standard unit. So if we want to convert from one unit to another, we'll have to use some identities, something that we know. So if I write identities, so there are many identities that you already know. Let me write some as far as time is concerned. I'll say in 1 year, it equals, let's just say 365 days. Okay, I'll say in 1 day, that's equal to 24 hours. I'll say in 1 hour, that equals 60 minutes. And I'll say in 1 minute, that equals 60 seconds. So with all of those things right there, and I think everybody who's looking at this knows those identities because it's something that we live with. It's not a new thing like metrics might be new. So those type of identities people understand. But if I were to ask you to convert, let's say if I were to ask you to convert 1 year into standard units, how would you do it? So if the question was convert what would you do? Well, the way I would do it is I'd basically write down what I'm starting with. I would write down 1 year, and then I would start to convert, and I would use these identities that I already know about. So to do this, let me erase these identities. I'd write down what I know. I know this. I'm starting with 1 year, so I'd say 1 year. Okay. Now, what I want to do is I want to multiply it by a fraction that has the top and the bottom meaning the same. So what I mean by that is I'll say in 1 year, and I'll say that there's 365 days. Okay. And from what I've just done, the unit of year will cancel out top and bottom. Then I'll say days. I don't want days. They're not standard units. So I'll say days. I know something about days. In 1 day, there is 24 hours. So days can cancel out because, like math, if you have a fraction with the same thing on the top and the bottom, they cancel out. Keep going with this. What do I know about hours? I could say in 1 hour, there is 60 minutes. The unit of hours cancels out. And then I could keep going and say, how do I get rid of units of minutes? Minutes will be on the top here. So in 1 minute, I'd say that there is 60 seconds. And the unit of minutes cancels out. And when you see, when I multiply all these numbers, you just take your calculator and say 1 times 365 times 24 times 60, and you'll get a number. So you get a number of 31,536,000, and the only unit that's left, every other unit has been canceled out. The only thing that didn't cancel out is seconds, and that is how much time is in 1 year. So that's how to do some problem like that. Okay. So we have something called length identities, and the length identities are basically half of them are things you already know. So I could say if I had 12 inches, I would have a foot. I could say if I had 3 feet, I would have a yard. I could say if I had 5,280 feet, I would have 1 mile. These are a lot of different identities that many people know. Not a whole lot maybe know just off the top of their head about this, how many feet there are in a mile. But then we have these metric identities. So I could say in 1 meter, I have 100 centimeters. I could say also in 1 meter, I have 1,000 millimeters. And I could also say in 1 kilometer, in 1 kilometer, I have 1,000 meters. So I talked about this earlier. If you took 100 small centimeters and added them up together, you'd end up with the length of a total meter. If you took 1,000 tiny millimeters and added them all up together, you'd end up with the length of 1 meter. And a kilo means 1,000. Just that word by itself means 1,000. That's one of the prefixes I talked about that was on page 10. So a kilometer, kilo just means 1,000. So this just means 1,000 meters. So I've written it here. Instead of 1K, I've written 1,000 meters. Okay. And what connects one to the other? Well, what connects them is there's an identity. And that identity is in 1 inch, I have exactly 2.54 centimeters. So that's an exact identity. So by writing these down and knowing how to use these, we can convert any length into standard units. If I were to say convert a height of 5 foot 10 inches to standard units, what I would do is, first of all, these are mixed units and they're both length, so I can't deal with different mixed units of length. I would have to say in 5 feet, what would I say here? I'd say in 5 feet, and then I can multiply that. And what do I know with one of the identities I just erased? I said in 1 foot, you have 12 inches. So you see the unit of feet cancels out, and 5 times 12 gives us 60. And the only thing left is inches here. So we have 60 inches. But that's just the 5 feet piece. We also had a person who's 5 foot and 10 inches. So they're 60 plus 10. So we're going to start this way. We're starting with 70 inches tall. So we have a person who's 70 inches tall. How would we convert that? Well, multiply it by a parentheses. Get rid of the unit of inches. Inches is on the top here, basically. So I could say in inches, I know in 1 inch, there is 2.54 centimeters. Okay, the unit of inches cancels out. Keep on going. I could say in a centimeter. One of the things I know is 100 centimeters is 1 meter. So I could say, multiply that, and the centimeters here and the centimeters here cancels out. And the only unit that didn't cancel out yet was meters. So if I multiply those together, the answer comes out to be 1.778 meters. The marker's not perfect there. So if you're using everything that you know, one of the things I know is when I was younger, they talked about a meter is approximately 3 feet. So in my life, most people I know are on the order of 6 feet, give or take a little bit more, a little bit less. Most people actually I know. So this is a little bit less than 6 feet. So 1 meter is approximately 3 feet. So that means 2 meters is approximately 6 feet. So this is just under 2 meters. So that's telling me that this person is just approximately under 6 feet, which I know 5 foot 10 is approximately that. So I'm using everything and I'm trying to evaluate my answer, and evaluating the answer, it seems very, very reasonable that that's going to be the person's height. So if I were to ask to convert 55 miles per hour to standard units, well, now these have 2 different types of units, so I only have to pick one at the start and then just deal with one. So what I might do is this. I might write down the start. I have 55, and I have miles per hour. So I want to get rid of one of them. I'll get rid of the miles. So I know in 1 mile there is 5,280 feet. The miles will cancel out. And then I can say, as far as feet goes, in 1 foot, I have 12 inches. And the unit of feet goes. And keep on going, and I can say, in 1 inch, I have 2.54 centimeters. And the unit of inches cancels out. And then I keep going, I could say, in 100 centimeters, I have 1 meter. And the unit of centimeters cancels out. And I'm at a standard unit, and the standard unit of length is meters, so I'm at the standard unit. So I can stop canceling unit meters, but you see the hours here is still involved. So what I have to start to do is I have to start to multiply it by units. that will get rid of the time. So there's an hour. It's in the denominator. So if I multiply over here and put an hour in the numerator, in 1 hour, we have 60 minutes. Squishing this in a little bit. And the unit of hours on the bottom will cancel with the unit of hours on the top. And also, minutes is on the bottom, so I'll put minutes up here. So I'm going to squish it. 1 minute. What do I know about that? It'll give me 60 seconds. Okay. So the unit of minutes here will cancel out with the units of minutes there. And the last unit that didn't cancel out is 60 seconds. So you can see the only thing I have left would be this unit right here and this unit. And those are standard units. Those are meters over seconds. So if I do my math out, I take 55 and multiply it by 5,280 and multiply it by 12 and multiply it by 2.54 and divide it by 100 and divide it by 60 and divide it by 60 again. I will end up getting 24.58 meters per second. And that is my standard unit for when I converted 55 miles per hour into meters per second. That's what I get. And that's correct. Okay, so here's my rule of thumb, because we don't live in a world of meters per second. So when we talk about speeds, typically people talk about in terms of miles per hour. So my rule of thumb is when you're doing this physics stuff and it's new to you, whenever you get a unit of meters per second, it is going to end up converting into, whenever you get a unit of meters per second and you want to evaluate it to see if it makes sense to you, my rule of thumb, so here's my thumb, thumbs up, okay. My rule of thumb is it's approximately 2 times. So if you were to have 20 meters per second, it's approximately 40 miles an hour. If you have 30 meters per second, it's approximately 60 miles per hour. The exact value would be in 1 meter per second, it equals 2.236 mph, miles per hour. But I'm not asking you to convert it this particular way. I'm just saying that when we do our math and we do our word problems, we evaluate everything, and to evaluate them, we should see that 1 meter per second, it's approximately 2 miles per hour. So all of our word problems will be dealing with speeds in terms of meters per second, and you have to come up with an interpretation of, is it a reasonable number, a reasonable value or not. The last thing we'll be doing here is Chapter 1, Section 8, called Dimensional Analysis. And with dimensional analysis, we basically will be just looking at the units, and it helps us with our physics formulas and make sure we have the right formulas involved. So what do I mean by that? You don't know many physics formulas yet. You don't know almost any formulas yet. But let me give you a formula. There's a formula here which says delta x equals v initial t plus 1/2 a t squared. And that's just a typical formula. Every one of those symbols means something different. So displacement is what we mean when we say delta x, and that's a length, and that has units of meters. And t is going to be for time, and that is going to have the units of seconds. And a is acceleration, Okay, so the symbol will be a letter A, and the unit we're going to use will be meters over seconds squared. Okay, so if you use dimensional analysis, we'll be able to see if things are working out okay. Okay, because in math we can only add things that are like terms. So you see, since this thing here is a unit of length, unit is going to be meters, then this product here has to come out to be meters, and this product here has to also come out to be meters. Otherwise, you couldn't add those together. So let's just check and see if they do come out to be meters. So the idea is displacement has a unit of m, meters, some number. Velocity has a unit of, I didn't write that one down, did I? V is for velocity. So velocity is units of meters over second. T is a time, has units of seconds. Plus 1/2 is a coefficient. It doesn't do anything as far as the units are concerned. A has a unit of meters over seconds squared. T has a unit of seconds, which is being squared. So if we go through this, nothing happens with the m here. Now, when we take meters over seconds, we multiply it by seconds, it's almost like this is over 1. So you have meters over seconds times seconds over 1. The seconds can cancel out. So this would just be left with meters. Plus, now on this one we have meters over seconds squared. And we're multiplying it by seconds, and that's seconds over 1, basically. So when we see it squared, we have to square the top and the bottom. So seconds on the top would become seconds squared, and the 1 on the bottom doesn't change. And if you have the same thing on the top and the bottom, they cancel out. So we're left with meters equals meters plus meters. And this makes sense because in math, we learned that we can only add like terms together. So this V initial stands for the initial velocity times time, and this A is acceleration times time squared with that coefficient. They don't look the same, but they basically, when you take the product of those two, it means meters. And when you take the product of these ones, it means meters. And if you had so many meters plus so many more meters, you can add them up and your final answer would come out to be in meters. So this idea, again, it's called dimensional analysis. And it basically means that when you're using a physics formula, what you should be doing is you should always be using a unit with any number whatsoever. Okay, and that's basically it for chapter 1.